Welcome, SpaceChem Tournament contestants. 2017 SpaceChem Tournament Round 6, Air Conditioning Without Anthropogenic Global Warming. So this was intended to be the hardest of the medium puzzles, but a lot of people said they found this one harder than the next one, masochism. And there are several reasons for that. So this is based on some real chemistry. In the 1980s, scientists discovered we had a problem with our refrigerants stripping the ozone layer from the planet. A popular refrigerant in automobiles was known as R12, but unfortunately, automobile refrigerant or automobile air conditioning is pretty leaky, and it was releasing a lot of R12 into the atmosphere, which was destroying the ozone layer. So they moved to a different refrigerant called R134A, and that has we've seen our ozone layer mostly restored. It hasn't fully recovered yet, but it's gotten a lot better. But R134A has another problem. It contributes to global warming. So the search is on for another refrigerant, and this one right here, HFO1234YF, is one of the first ones. Much lower global warming potential than R134A. Works about as well, and also does not damage the ozone layer. So how do you make this? So many of these refrigerants have fluorines all over the place. Well, we start with an ethane molecule, and we replace a lot of the hydrogens with fluorines. So there's no oxygen in this process. And the problem is, in this puzzle, we have to do several things. Firstly, replacing the hydrogens with fluorines. Previous puzzles had 2 bonders. This one you get 4 bonders, which might seem luxury, but after you start looking at the problem of replacing the hydrogens with the fluorines, the hydrogens need to be carried to the output zone so you can get rid of them. The fluorines are in the opposite input zone, other side of the reactor, and you had the problem of, if you were going to bond the fluorines here where they're input and debond the hydrogens where they're output, then you would have to put 2 of your reactors in the input zone and 2 of your bonders in the input zone, 2 others in the output zone. And then if you only have 2 bonders to work with, that makes it awkward to move the atoms around. You have to break that fluorine bond, assuming you've already stripped the hydrogens off. Then you've got to move one of the fluorines off, move a carbon on, bond it, move the carbon, the newly bonded fluorine off, and then bond the other fluorine in. We will look at pseudo-dude solution later, and it does basically that. And then you have to do something similar with the hydrogen. You get over here, you debond one hydrogen at a time. So you'd have a carbon and a hydrogen, take that one off, move it off, move another hydrogen on, take it off, move the carbon out of the way, bond the 2 hydrogens together, and output them. So what a lot of people did, instead of putting 2 bonders in the input zone and 2 in the output zones, they kept all 4 bonders together, and using bonder priority, you could do an instant. You would break these bonds, and then when you rebond with bonder priority, you get the 2 hydrogens to bond to each other, and you would have this happen in the output zone, so you can just output it right away. I didn't see any solutions. Most people put the bonders in or near the hydrogen output zone so you could send the hydrogens out without having to carry them. I didn't see any solutions where people were carrying the hydrogens to the output so that they could do the 4 bonders in the fluorine input zone. It's because there's more hydrogens to get rid of. So here is JFB 1337 solution. And because we have the 2 bonders, we have to strip the hydrogens off one at a time. So he's using the bonders separately. Kind of move it over. We're getting our next one, and we're building a big chain. So this illustrates the next problem. You have the problem of fluorines and hydrogens only being able to bond once, only one bond, so that carrying them around is difficult. And then you had the problem, this output is a backbone of 3 carbons, and your input is 2, so you have to input 3 ethanes to generate 2 of the refrigerant, which means you've got to handle the midpoint somehow. Now, what a lot of people did was they would break off. You get 2 ethanes in, you have 4 carbons. We're going to store one of these somewhere in the reactor out of the way. This will have to move before we can input another ethane. And now we're going to strip off more hydrogens. Have to strip off another 2. So fairly complicated. Look how busy this particular solution is. Now we're down to there. Now we've got to add the fluorines. So let's see how this solution does that. All right, we're going to put one fluorine on that pair of bonders and the other fluorine also on that pair of bonders. And we spin the molecule around. Attach that fluorine. Now we need the double bond. So a lot of handling to get this onto the bonders. There we go, finally. And then we've got to position it in the output zone. All right, send it on its way. Now we've moved this out of the way of our 3rd ethane input. So we build our backbone of 3 again, and we're going to strip those hydrogens off, same as before. So this solution was fairly slow because of the way we're stripping hydrogens off one at a time. Stripping them from the opposite side, and you've got to carry them. Instead of forming the molecule in the output zone, you have to carry it at least one space, the way this is designed. All right, so this is JFB 1337 solution. Score 1.2, one of our slowest and symbol heavy solutions. Yeah, that is our highest symbol count, 150, and our second slowest solution, so a score of 1.228. Next up is Twistia with a score of 1.233, and then Cactus with a score of 1.273. And they have the next highest symbol counts, respectively, 144, 139, and also Twistia's is the slowest at 2064. Cactus at 1855. Also, on this puzzle, we were scoring Waldo path. So these 3 solutions used almost the entire reactor, 79, 78, and 79. So they do not score very well in that category. 80 is the maximum it could be. So let us have a look at Twistia's solution. All right, we have 4 bonders in the hydrogen output zone, which allows us to do, well, we're going to strip those off. What a lot of people did was put this cluster of 2 carbons and 2 hydrogens on the bonders, but Twistia's solution did not do that. Instead, he's getting the end pieces off. Now, for the last 2 hydrogens, he is going to use. This was very common. A lot of solutions did this. D-bond, and when you rebond, hydrogen can only connect once, so it connects to the other hydrogen if we have the binder priority correct. And now we can't output it just yet. We've got to prevent this carbon, so we grab hold and then we output. So there's 2 carbons, and now we're going to add fluorines. So we get in the corners again. And now this, you use bonder priority again. Strip the hydrogens off, in this case with the carbons horizontal, and then turn them vertical so that our bonder priority favors them forming. So we rest this here. We grab another 2 fluorines, drop them in, debond, and bond. So now we've built our 2/3 of our output molecule. So this one, the first one we were saving a line, hydrogen, carbon, hydrogen. This is an L-shaped. Okay, we need our 1 more double bond. We get that right there. And then just a straight shot up, send it out. We'll find out what that's for soon enough. It's to handle, no doubt, the second and third ones, because that counts to 3. Right, stripping off the next hydrogens. Save those. The chosen location just barely out of the way. Stick it in the upper left corner of the reactor. Now all we have to do is retrieve this stored piece. So first position this on the bonders, run way up here, grab it. Okay, we only have 1 bond, so that's what this is for. Come back down and get a second bond. And now this is to edge this output molecule over 1 at a time. Still got to get that last fluorine in there. All right, only 13 solutions. So this one is number 12. And thanks to a lot of travel time, very slow. Next up, cactus. Another one. Interestingly, our 4 bonders are over in the input zone. So let's see. That means we've got to carry these hydrogens to the output zone. So this solution is stripping the hydrogens. This is a rather unique way. The 2 hydrogens left over are on opposite sides of our carbon backbone. So that was an interesting choice of order. Okay, save our 2 carbons. Now add the fluorines using our... Okay, but we did not really use bonder priority because the fluorines got there first. Well, we did. They did bond there. And then we had a second, that created a second bond on the carbons, which we got rid of immediately afterwards. And now we got to put 2 more fluorines on. Would have thought the blue one would do that, but it's red. And now with 2/3 of our molecule built, well, that can't stay there if we're going to output hydrogens. Okay, so stripped off just enough. Here is the other half of our backbone. We need 1 more bond. Well, look at all the handling to get this, keep this out of the way. And now finish up with our second output. Yeah, a lot of running around. There we go, finally. Bond, one more bond, which we will get as we rotate just to get that bond. Right, so 1855, 139, the best yet on cycle and symbol count. Still very high path count. Now our scores take a jump. In 10th place we have ATommate with a much faster and a little bit lower symbol count solution, and a little better on the Waldo path. All three categories score of 1.639. So let's see what he did. Okay, yes, more clear space in the reactor. Our 4 bonders are in a square in the output zone so that we can strip our hydrogens off and send them out. Only sent away. Now we're stripping them. So if you get the 2 sides, then you've got to do something to get rid of the 2 ends, and it just takes time to do that. You've got to. So now we've turned the carbon backbone. It was horizontal for stripping, now it's vertical for adding the fluorines. And now we need to add the 3rd carbon, so we have not broken this one apart yet. There it comes. And double bond with red and blue both doing that. And here we're saving our extra piece. Top middle of the reactor. So a lot of solutions had to do this because you have the 4 bonders over here. You have to drag the fluorines all the way across the reactor, which takes time. It takes cycles to do that. All right, there is our solutions. 2 molecules. So much faster and fewer symbols. Next up is counterpoint 1.650. And so we see cleaner yet. He had our best Waldo path, 62. So this is interesting, an L shape. One thing I have been putting in every puzzle where it makes sense to do so is a sensor. So that was an interesting way to peel off the hydrogens. Add our fluorines to the corner. We're storing our excess over here. Now we've still got to split that. Okay, so we have added it on first. Then we get rid of it and make our double bond. Alright, so we have a straight line. Let's see how he did the hydrogens again. Strip off the corners, but oh no, we're stripping off the ends first so that they are already in there and just have to output them. Then, because the bonders are not in a cluster of 4, so we're getting the opposite hydrogens from the opposite sides. Now we can, well, we could have debonded them both right there, but no, we're going through our loop again so that we take one off, take the other off. Add our hydrogens on. So slower, but quite a bit better on the symbol count, so this scores ahead. This was our 9th place. Next up, 1.735 points is Zig. Our fastest yet, 1070. A little worse on the symbol and the Waldo path, but quite a bit faster, so it scores better. Let's see what Zig did. Alright, cluster of 4 bonders in the output zone. Start off, strip. Alright, so the first input is intended to be our one that gets split. bit of dancing around, trying to keep the excess from running into the piece that we're going to bond on. And here's this. I'm going to take a closer look at that dancing up here on the next pass. Let's have a look at that again. Okay, we have created 2 with our 4 fluorines. Now we need to break this apart and attach that. So this needs to be pulled out of the way. Now our debonder is in place. Okay, we break our bonds. Now we leave this in place. We will drag this over and attach it, but this has got to be pulled out of the way first. And so this is being bounced back. Tricky timing right there. Simply to give the blue Waldo time to carry the extra piece out of the way. Where it will wait on the sensor. There it comes. And we are dragging yes. All right. Quite a bit faster. Next up, the score of 1.763 aperture. And let us see what aperture did. Okay, we see a much more compact reactor here. So this is our best Waldo score yet, 52. However, it's 106 symbols, almost the same as the previous, and pretty slow, 1449 cycles. Let's see how this works. We have put our square of bonders. Only 2 of them are in the output zone. So to do our little trick, okay, we are doing vertical. Let's see how he gets rid of. All right, he's going to. Okay, 180 rotate. Get the next 2 hydrogens. Then we've got to get the end pieces. What are we doing with the end pieces? Okay, rotate, peel off one, rotate, peel off the other. So the hydrogens are all being built on the pair of bonders that are in the output zone, which gives us no problems with having to wait for the carbon. We could have output that sooner. There's no rush. So now we have our 2 carbons. And one of those carbons is right where the fluorines must come in. So they are going to have to move before. Now that we've stripped the hydrogens off 2 of them, well, we've got to leave 2 or 4 hydrogens left over. And there they are. All right. So this solution adds the fluorines on last. We have built our backbones. Okay, so because they were vertical to strip the hydrogens, now they are horizontal to add the fluorines. And now it's just transport it to the output zone. Do the second one. So we're going to do the fluorines again. Right. So that was aperture. And now our scores take another jump to 1.949 tough thought solution. Tied him on the Waldo path, and this is our lowest solution symbols yet, 92, and it's reasonably fast, 1168. So here's tough thought solution. One of the remarkable things about this is look at the number of sensor commands in here. 1, 2, 3, 4, 5 hydrogens, 6 hydrogens, and 2 carbons. 8 senses total. I think that that's the record for the most sensors. He positioned the bonders in the middle, which means that we need to carry the hydrogens into the output zone. It's only one cycle away, but still you have to carry them. So peel off 2, using bonder priority that time, peel off 2 more, carry it. Leave those 2 hydrogens. Okay, and yeah, the order is interesting here. Fluorines, then some more work, and then the other 2 fluorines. And we can't output this yet until we've grabbed hold of that. Once we grab hold, now we can. We're left with a single carbon. And we're going to add the fluorines to it first. Now strip off hydrogens. Add the last 2 fluorines. And done. So a bit slow, best symbol count yet, and best Waldo path yet. That was our 6th place solution. In 5th place, breaking into the 2 points now, 2.058 Leylite, with our fastest solution yet, 657, so 113 on the symbols, but high on the symbol count, and 60 on the Waldo path. So this one gets 5th place. There it is. And let's see, all right, 2 bonders in the output zone and 2 of them out. Here's our sensor. So we begin by stripping off 2 hydrogens off that. So this is going to be a split to provide the 3rd carbon eventually. And now that was an interesting way to put the fluorines on. Bring that down, rotate, get our 2nd bond, keep moving that around to get it out of the way. Notice also, this was saw this in several solutions. We started with, well, we'll just look at it again. So we got to clean this up. Grab hold of that last one, add it on. Okay, though these 2 carbons that are going to be split and put on separate outputs, notice how we strip 2 hydrogens off and we have 2 L shapes, but they are rotated 90 degrees. So what we do is the first one, leave it there in position, and then the extra we're going to carry up here and we're going to rotate it 90 degrees so that now it is in the same orientation as the one we just attached, so that when we build our even numbered molecule, this is already oriented correctly. That's actually the way I did it in my solution as well. Right, much faster. 5th place, congratulations. In 4th place, Blue-Eyed Rat, 2.195 points. Our best Waldo count yet, 49. And this is our lowest symbol, 69, which makes up for the fairly high cycle count, 1312. 69 symbols. Let's see, how did he do it in 69 symbols? Now what's interesting here is this could have been an even lower symbol count, but Blue-Eyed Rat wanted to keep that Waldo path down. So right here, this could have been that, and we remove 2 arrows, so we get our symbol count down to 67. But then our Waldo path goes up by 2, because now we're traveling through those. Also, right here, it could have been made a little faster this way, but then red is traveling through this spot, so that increases our Waldo path. So Blue-Eyed Rat thought it was worth Probably worth losing 20 cycles for a Waldo path, yes. Whether it was worth 2 symbols for 2 Waldo path is more debatable. But this is entering. Let's see how this works. So we have 2 of our bonders in the output zone. So we are doing our vertical orientation to debond and bond. Okay, he is taking. So this is going to be the one that gets split between the 2 outputs. Drag our fluorines over. No? Okay. He got rid of those hydrogens, so this one will be part of our output. We've got to add, let's see how this works. Well, that can't be right. Okay, we're stripping off the last 2 hydrogens. All right. We've just taken our time stripping all the hydrogens off. And now these 2 are the ones that are going to become the split to become the hydrogen. So here's this. Add that on. So this is how we got such a low symbol count. We're using this pathway here to strip hydrogens and to break our backbone. Split our backbone. Now, okay, so we drag that over. No, we are not going to use those hydrogens for this. We're going to strip them. Going to strip those 2, same as before. And now we put this together. Okay, very nice. So let's see what that would have done to his score. What if Blue-Eyed Rat had increased his Waldo path by 2 and saved 2 more symbols? 2.164 versus 2.1. So it was absolutely worth it. Well, actually, the reason his score went down is because he already has the best score. All that changing his symbol count do is lower everybody else's score. So he lost 0.031 points, but other people 2288 2308. Okay, so Rezunes would only lose 0.2 and Blue-Eyed Rat would lose 0.031. So it was worth it to spend 2 symbols to save 2 Waldo path. Next up, in 3rd place, Rezunes 2.308 has a good Waldo path, 52. Fair number of symbols, 100. That's kind of average, and fast. So let's see how he did it. Okay, 4 bonders in the output zone. Okay, stripping off. Now that's nice. We briefly put the 2 ethanes together in a box of 4 carbons with hydrogen stuck on them, and split that and use that bonder priority. Horizontal to strip the hydrogens, vertical to add the fluorines, and then add that last bond as we drag across. Now pick up our excess and add that on. So let's see what that handling one more time. When we make 4, okay, get rid of those 2 hydrogens. Briefly have 4 carbons on the 4 bonders. Carry that one off. And when we come back around to build our even molecule, Yes, we have rotated this one so that it is in the same orientation as the one we left. Alright, 604, 100 symbols. Second place, Sir Baldrig. With our fastest solution, 524 cycles. Pretty heavy on the symbols, 110. Decent Waldo path, 56, 2.324. So let's see what he did. 4 bonders in the output zone. Okay, so we used bonder priority to strip the top 2 hydrogens. Then, as we passed around a corner, we stripped the N and this, leaving those 2 hydrogens. Now we are going to put the fluorines on, since horizontal, using the bonder priority, make sure that the fluorine connected to the carbon over here rather than back to the fluorine. And then we do another corner to get rid of those 2 hydrogens. Alright, and we're now horizontal to strip, vertical to add. Now what are we going to do? We are going to build another carbon with 4 fluorines. We are not finishing either of our molecules yet. We have not yet output anything. And well, except for hydrogens. So now we have both of these finished. We need to keep 4 of these hydrogens, get rid of one of those, park that down there. Need our second bond, there it is. Get that in position, ready to go. There, and so almost finish them, then bang bang, 2 of them out. That's how this is so fast. Would this be a fantastic case of delayed gratification? Let us see. What cycle was it that we sent the first output? I mean, we had to wait a long time to see one output. Here we go. We're not in position yet. Cycle 92 before we saw our first output. But then cycle 105 gets our second, so only, well, 104. Only 12 cycles later to get the second one. So very nice, 524. Second place, congratulations. In first place, Darius1 said he had a lot of fun with this puzzle, and just look at this. 2.5, that's a 0.2, 2.533, 0.2, and a little more ahead of second place. So Darius1, congratulations, you won this by a huge margin. You have the best Waldo path by a lot. Second best is 49, yours is 39. And you managed to keep your symbol count very low in spite of that. So that's the second best symbol count, 84. And your solution is still pretty fast. It's not the fastest, but it's very fast. So let's see what you did. Even sent in pretty early. So look at this. This is one of the things I love about doing a Waldo path is it looks like you've put this thing in shrink wrap and just crushed it down in there. Alright, our 4 bonders are in the output zone. And so we are doing the vertical orientation to strip. In this case, instead of doing a 180 to get the hydrogens over there so we can do a bond-debond, we are simply, because all 4 of them are in the output zone, we can just slide over. So the first 2 hydrogens are output here, the next 2 are output there. Now we brought in the fluorines early, and they just sat there. Now they've been collected. Okay, so we did our strip of the end. Okay, do our rounding the corner to get the 2 fluorines on. Bring in the next 2 fluorines. Vertical to strip, horizontal to add. And now, how are we going to handle this part? Strip off those 2. Alright. Store that right there. And we can do that because we're bringing the fluorines down before we come over. second set of fluorines. Okay, send blue to grab this. And here is our rotate. Get that in the same position. So store that up here, bring it back down, connect it. All right. So congratulations, driest one. Well done. Now we had a couple of other solutions. This is the one that I came up with and kept refining. So this is actually not the final version that I came up with. Move some things around. Yes, I am doing a loop here, and I got that into one loop. Not a very good solution. It's reasonably fast, but I have a better one. Well, since I can't find where I stored my solution in the puzzle game, I'll use my SpaceChem in a browser website. So this is my best solution. And what it does, we're just doing spin it around twice. Store that up there. Yep. Get rid of the hydrogens horizontally, do a double rotate to get the end pieces. I've tried to save time by dragging the fluorines over earlier. And that does not work because both walls had hold of the molecule for an instant, so this broke down. But that's the idea here. This one, 651, 87, and Waldo path of 54. For a score of 2.320. So if I was playing, that would have been third place. And finally, let's look at Pseudodude's partial solution. It's a shame that he didn't quite get this working. It almost works. This is a really unique one. We have another L shape here in the input zone in the middle. And the reason for that is because look what he's doing here. He's stripped the two ends off. And you notice that they are, there's an empty cell between them. That is because now the other hydrogens he's going to strip off in that fashion. Move a carbon hydrogen line in there, debond and take the carbon away. So there's a hydrogen output, which means then that we've got to drag one of the hydrogens over to connect it. So that's a unique way. Of stripping the hydrogens. Well, but he had to do a lot of transport. So how do we put the fluorines on? Okay, so that was very nice there. We get the fluorine on the end because we started our backbone. We've already got the double bond. And he is hooking his fluorine up to this carbon rather than that one because he's going to position this carbon on that bonder. Well, first he's going to drag a fluorine down and split it. And now this carbon comes in. We add our last two fluorines. And output it. Then we're going to do same thing, but we have this extra piece sitting down here. This extra line. So let's see. So there it is. We have got two outputs done. So why doesn't this work? Well, we have a problem with just couldn't get those flip-flops reset correctly. So here we are, back to our start position, more or less. Where's the red start? There it is. Well, the red start is over here. So okay, yeah, this is virtually our starting position, but in this case, we only had that beta input just right at the only time at the start. And the problem is that this flip-flop is active, whereas at the start it was not. And so what happens is let's get to our second output again. Okay, same as before, but with this flip-flop active, well, it needs to be, no, it doesn't need to be active. There. That's what happened. Because it was active, we stored a piece down there. No? Well, anyway, we'll have to study this a little bit to see if it could be repaired. That's too bad. Crash it. Cycle 321. Well, thank you for sending that in anyway. It was a unique solution. I haven't seen it, and none of the others look quite like this. And we shall see you. I am out of time to do further video recording right now, so I'll have to tackle masochism maybe in another couple of days. I will see everybody later. Then we'll do Noble Fission, which it sounds like everybody really liked Noble Fission. Favorite puzzle? Think about which puzzle you like the best, because now that they're all out, we can vote on this. Until next time.